there's this really neat idea that you encounter in E2 reactions, and we'll see it other places as well, but it's this concept of regioselectivity. This is where the same reaction can occur at different parts of the molecule, and you have to decide what part of the molecule is going to react, which region of the molecule is going to react. So let's look at an alkyl halide. Here's a molecule. We're going to react this with a base. Let's keep it simple and quick to draw. Sodium hydroxide, probably running in water. And this is we have a strong base. We have a halide. So we're going to do an E2 reaction here. So as it turns out, the carbon bearing the halogen is the alpha position, and we know we're going to remove a beta hydrogen. But there are two different beta carbons here. I could bring up a third beta carbon, but by symmetry, this one is the same as that. So we're just going to focus on the two that are on the right. So both these carbons have hydrogens. I'm not going to draw them all in, or it's just going to get too crowded. As it turns out, the major beta hydrogen to remove is the lower one, and we'll call this A. And this hydrogen and its other two that aren't drawn, we'll call those B. And so what happens is our base attacks this hydrogen, as we saw before. The electrons kick in, and we can kick out our bromide, and that's going to give rise to this compound. We'll call this compound A because it came from the removal of beta hydrogen A. We could also show a mechanism where we instead remove beta hydrogen B. We go through the process, drawing that, you get this as the product. Now these are different. These are isomers of one another. They have the same molecular formula. Specifically, they are called regioisomers. And they have special names. Compound A is called the Zaitsev product, and compound B is called the Hofmann product. And we'll say how they got those names. The Zaitsev product in an E2 reaction is typically the major one, and Hofmann is typically the minor one. So why is Zaitsev the major? Well, if you look at the alkene in compound A, the Zaitsev product, and I'm going to fill in one of these, the hydrogens. Let's go to B and fill in those hydrogens as well. When you look at an alkene can have around here. An alkene can have up to 4 different R groups on it. If we look at compound A, that alkene has 3 R groups and then 1 hydrogen. So it has 3 non-hydrogen groups on the alkene. That makes it a trisubstituted alkene. Compound B, on the other hand, has 2 non-hydrogen groups attached to the alkene carbons, 2 non-hydrogens, therefore 2 hydrogens. And so this is a disubstituted alkene. As it turns out, trisubstituted alkenes are more stable. The greater the substitution on the alkene, the more stable that alkene is. So this is normally the favored product. It's not surprising. You very often when you run a reaction, you form the most stable product. And that is the reason why the Zaitsev product is typically the major product, because the Zaitsev product is the more highly substituted alkene. In this case, it's a trisubstituted alkene. Is there any way to make the Hofmann product? Why, yes. Yes, there is. So let's redraw our alkyl halide. And there's a specific base that people use if they want to make the Hofmann product. It's called T-butoxide. Okay, so we put a T-butyl group on our O-. Instead of a little H or a little methyl or ethyl, we put a nice bulky T-butyl group. And we'll have a solvent of T-butanol. This makes our base very hindered, and our base actually has a hard time attacking that more crowded hydrogen. So it goes after the less highly substituted hydrogen. the less hindered beta hydrogen. We kick out the bromide, and we observe as the major product the Hofmann product. So, how do you do this? You specifically use a different base, a very special base, T-butoxide, because it's very hindered. So we can actually control the regioselectivity of the E2 reaction. If you want the more highly substituted alkene, use your regular bases like hydroxide and methoxide. To get the less highly substituted alkene, the Hofmann product, you can use a more hindered base, specifically T-butoxide.